This technique is useful for characterizing the kinetics of oxidation and reduction of organic compounds and predicting their behavior as an active compound of light-emitting diodes, solar cells, or batteries.
The main advantage of impedance spectroscopy is that it allows separation and individual analysis of different parallel processes according to their AC responses.
To begin, dissolve 0.4 millimoles of tetrabutylammonium tetrafluoroborate and 4 × 10⁻³ millimoles of the organic compound of interest in 4 milliliters of dichloromethane. Pipette 2 milliliters of this working solution into a 3 milliliter electrochemical cell, such as a glass V-vial, and close the cell with a gasket cap. Store the remaining working solution for later measurements. Next, mount a polishing cloth on an immobile support and moisten the cloth with several drops of 0.05 micrometer alumina slurry. Polish a 1 mm diameter platinum disc working electrode for 30 seconds using moderate pressure. Afterwards, rinse the polished working electrode with DCM 3 times to remove residual alumina particles. Then, insert the polished electrode into the electrochemical vial through the gasket cap. Next, obtain a platinum wire counter electrode and ignite a butane torch. Anneal the electrode by carefully holding it in the flame just until it starts reddening. Anneal a silver wire reference electrode in the same way and allow both electrodes to cool. Then, mount the wire electrodes in the electrochemical cell through the gasket cap, being careful to keep the electrodes from touching each other. Connect the 3 electrodes to the potentiostat. Equip the electrochemical cell with an argon gas line and bubble argon through the working solution for 20 minutes. Close the flow of argon before beginning the measurements. To begin the initial characterization, open the cyclic voltammetry program in the potentiostat software. Set the initial potential to 0 volts, the minimum potential to -2 volts, the maximal scanning potential to 2 volts, and the scanning rate to 100 millivolts per second. Acquire the voltammogram of the working solution. Note the potential values at the maxima of the anodic and the cathodic peaks. Calculate the average of the peak potentials of the anodic and cathodic peaks to estimate the redox potential. Next, use a spatula to add about 10 milligrams of ferrocene to the working solution in the electrochemical cell. Bubble argon through the solution for 5 minutes to ensure complete dissolution of the ferrocene. Then, in the cyclic voltammetry program, change the minimal and maximal scanning potentials to -1 volts and 1 volts respectively. Acquire another voltammogram, which will show a small, reversible ferrocene trace. Average the anodic and cathodic peak potentials of the ferrocene to estimate its reversible oxidation potential in the working solution. Then, determine the redox potential of the organic compound with respect to ferrocene. Lastly, to clean the electrochemical cell, fill it with DCM and empty it 5 times. Following characterization by cyclic voltammetry, place another 2 milliliters of the working solution in a clean 3 milliliter electrochemical cell. Clean the electrodes as previously described, insert them into the cell, and reconnect them to the potentiostat. De-aerate the working solution by bubbling argon through it for 20 minutes. Then, open the Staircase EIS program in the potentiostat software. Set a potential range of 0.1 volts on either side of the redox potential of the compound of interest for a total range of 0.2 volts. Set the potential increment to 0.01 volts, the frequency range as 10 kHz to 100 Hz, the number of frequencies in the logarithmic scale to 20, the wait time to 5 seconds, the AC voltage amplitude to 10 millivolts, and the measures per frequency to 2. Run the experiment and wait for the set of spectra to be collected. Once the experiment is finished, open the EIS Spectrum Analyzer program.
The demonstrated program is universal for impedance spectrum analysis. However, it's not necessary to use this exact setup, as numerous other software options can be used.
Import an automatically registered spectrum generated by the EIS experiment. Then, construct a simple equivalent electrical circuit for the spectrum. Set the initial upper and lower limits to 1 × 10⁻⁷ and 1 × 10⁸ for the capacitor, 2100 for resistor 1, 1100 for resistor 2. Then, fit the model. Repeat the fitting until the calculated values stop changing. If the R² parametric and amplitude values exceed 1 × 10⁻², test another EEC. For more complex EECs, set the initial upper and lower limits for the Warburg element to 50,000 and 10,000 respectively. If any parameter has error values exceeding 100% after fitting, remove that parameter and try another EEC. Once the spectrum has been fitted to an appropriate EEC, record the charge transfer resistance and the potential at which the spectrum was registered. Repeat this process for all registered spectra. Cyclic voltammetry of this organic compound revealed a reversible oxidation process at 0.7 volts versus ferrocene. Impedance spectra of the redox processes on the electrode surface were subsequently registered and analyzed. The impedance spectra were fitted with various equivalent electrical circuits to identify the best analog for the electrochemical process. The charge transfer resistance, represented here as R2, was extracted from each fitted spectrum. The inverse charge transfer resistance values were plotted with respect to electrode potential versus ferrocene, along with the theoretical dependence of the inverse charge transfer resistance on electrode potential. The standard electrochemical rate constant was then estimated by varying the equilibrium potential and the rate constant until a reasonable fit for the experimental data was achieved.
The demonstrated technique can be used jointly with other methods of investigating an electroactive organic compound when its redox properties are crucial.
Following this procedure, other spectroelectrochemical methods like ESR, UV-Vis-NIR can be performed to answer additional questions about changes in molecule structure caused by electrochemical processes.
While attempting this procedure, remember to account for other processes that occur in real systems that may complicate the obtained results. In case of irreversible reactions like polymerization, this technique cannot be expected to give reasonable results.
After its development, this technique paved the way for researchers in the field of charge transfer kinetics in organic electronics to better predict the redox performance of molecules and materials.
Once mastered, this technique can be done in 2 hours if it's performed properly.